chapter 5, here we go. Common types of chemical reactions. So last week we learned how to balance chemical reactions and we learned how to classify kind of an initial 5, the 5 I mentioned already. So here's 3 more ways to classify them. And they do actually overlap with the combination decomp, single double displacement, and combustion. So the types we talk about today, it could be a single displacement and it could be a precipitation reaction or a redox reaction. So they overlap. It could be both. One from the category last week and one from the category this week. So the first kind we're going to talk about is known as a precipitation reaction. Okay. So you guys are familiar with what a precipitation is because we talked about that like the very first week of class. It is a solid that is suspended in a solution or in a liquid. And when you have that, if you look at this picture on this slide, you see 2 clear beakers or beakers with a clear solution. And then when you mix them together, you get this bright yellow precipitate. It's a solid dispensed in a liquid. So this occurs, I'm just reading this bullet point here, when water-soluble reactants react to form one or more insoluble products, okay? And the insoluble product is your precipitate. So we call precipitates insoluble. They do not dissolve, okay? The insoluble product is the precipitate. So let's look at this reaction. Here's an example of a reaction. We have PbNO3, that is, how do you say that? That is lead nitrate, okay? Again, you're gonna need to really be sharp on your polyatomic ions for chapter 5. And what does AQ mean? Did anybody remember from the videos last week? What does AQ mean?
Aqueous.
Yeah, aqueous, aqueous, people say it different ways. It's just a solution that has ions or soluble things in it, okay? So we have lead nitrate, and then we have Ki. What is Ki? It is potassium iodide. I want you to get used to saying these things in your head as you read them. And then what do we form when these are mixed, okay? And that's these 2 beakers. We get KNO3, potassium nitrate. It is AQ, it's aqueous, so it is not forming a precipitate. But we also get PbI2, lead iodide. And you see this abbreviation? It's not letting me write. You see this S? That indicates that lead iodide is a solid, okay? And that is the precipitate. So here, indicating the physical state is crucial, okay? Without it, we can't easily know. There is a way to know. We're about to introduce another way to know. But it tells us which one's the precipitate. So if you can, or if you're asking yourself, if you read a reaction, you're like, okay, is this a precipitation reaction? How do I know? Well, if the abbreviations are given, and one of your products has a solid, has an S because it's a solid, then that's how you know it is a precipitation reaction, okay? Now, what if you're given a chemical reaction and we don't get any of those abbreviations? AQ, liquid, solid, what if we don't see any of those? Well, we have this next table right here. It is a list of solubility rules, so you can figure that out, okay? So let's look at this. You're going to have this for the exam, this list of solubility rules. You have it in your notes. I'll probably put it on the resources page for quick access. But just because you have it doesn't mean you're going to know how to read it. So you need to make sure you know how to read this, okay? So let's look at this. The column on the left, it says if it has any of these ions in it, so the ions listed in the left-hand column, if a compound contains any of these cations and any of these anions, it is soluble, period. Now there's a few exceptions at the bottom we'll talk about, but let's look closer. So we have these first 4 right here. These are all cations. So if a compound contains any of these cations, that compound is soluble, okay? This is for ionic compounds, by the way, not covalent. So we got cations and anions, and if the compound contains any of these 4, the ammonium, lithium, sodium, or potassium ion, there are no exceptions there, okay? Those compounds are soluble. They will not form a precipitate. We have 7 anions listed beneath that. Okay, the first three, so I'm going to draw a big red line under acetate. Those three anions right here, if the compound contains one of those anions, it is also soluble, no exceptions. It will never form a precipitate if it has that as the anion. However, the four anions down here, chloride, bromide, iodine, sulfate, these have exceptions. So your compound will be soluble if you have chloride, bromide, iodine, or sulfate in it, unless the cation are these listed over here. And there's only three you have to remember. There's 6 total, but actually 4 of them are there's really only 1, 2, 3, 4 that you have to memorize. So for example, let's say your anion is chloride, and your cation is silver. If you have Ag, which forms a +1 charge, Cl, if that is your compound, usually because chloride your anion here, it would be soluble, but because silver is your cation, this would form a precipitate. This would form solid, so it'd be insoluble. If you have another compound, let's say, I'm gonna erase. Let's say we have chloride is the anion, but magnesium is the cation, and therefore we need 2 chlorides. Magnesium is not an exception here, so this would be aqueous. Aqueous. This would be soluble, okay? Because magnesium is not listed over here with the exceptions. If we're looking at sulfate, same idea. If barium is our cation, BaSO4, you have a +2 cation, -2 anion, so you only need 1 each. Because barium is an exception here, usually sulfate means the compound soluble, right? Because it's under the soluble column. But because barium is your cation, now it's insoluble. It's going to form a precipitate. So that's how you read this. You'll have this table. Let's see how well you really understand it. I'm going to pull up our first poll, and I want to know, are these compounds soluble in water or not? Oh, man. You know what? I wrote it for the morning 1050 lecture, that poll, and I did not write it. You have to write them for both. Dadgum. Okay, well, I don't have the poll. Let's talk through these. So which of these are soluble in water? Let's look at the first one, CdCO3. If you have a periodic table, that might help you. Cd is cadmium. It's a +2 here. And let's go look at is this soluble or not? Is this going to form a precipitate or not? Well, I'm looking at my solubility chart. I don't see cadmium. It's not one of those top 4 cations, and I don't see carbonate, CO3. So what does that mean?
It's not going to be.
It is not soluble. That is correct. It would form a precipitate. You would
So does it have to be on that chart that you just showed us to be soluble?
Yes.
Okay, thank you.
Yep. So this would not be soluble in water. Okay. So what about lead sulfate? PbSO4, Pb is lead. Well, sulfate is on here. It's the last one down here, and it's under the column listed as soluble. But what do you notice over here? When Pb2 plus is the cation, that means sulfate is an exception. Okay, so that means this one would also form a precipitate. So this would not be soluble in water. So I'm going to zoom out for a second, and I'm going to be quiet so that you can do the next 3 on your own. So if you're unsure, if you're not sure how to go about this, give it your best educated guess. We're going to walk through them in just a second. Okay, maybe at least have a head start on me. Let's talk about C. We have Hg2, that's the mercury 2 ion, and we have Cl2. So chlorine, when it's the anion, usually it's soluble, but when it's combined with Hg2, 2+, it's not soluble. Usually it is, but because this is a cation, it's not soluble. So this is going to form a precipitate as well. So this would not be soluble. All right, Na2S, sodium sulfide. Well, if you're looking up here, it says sodium compounds are soluble, okay? And there are no exceptions. So yes, Na2S, sodium sulfide, is soluble in water. So you would see it AQ. Lastly, ammonium phosphate. Looking up here, ammonium compounds, these are soluble, and guess what? There's no exceptions, okay? So this one would be soluble, and it would be AQ. Keep wanting to write the Q first. Okay, so there's that. So questions on how to do solubility rules, questions on how to identify if something is a precipitate reaction or not. I'm reading the chat too. I was catching up. Someone said, can we offer more points? Dallas, you want more points? Which means more work. I'll have more bonus point opportunities for exam 2. Okay, I haven't decided what yet, but just the way we had a bonus point opportunity for exam 1, we'll have one for exam 2. It'll probably be more than 2 points as well. All right, what products will be formed, and are they soluble or insoluble? So we're going to do another practice problem. So I want you to look at this reaction, write down what products you get, write down if they're aqueous or going to form a solid, and then we'll balance it at the end. Okay, so first off, how do we go about this? Here's what I see. I'm looking at these reactants. What kind of compounds are these? Well, first off, I notice that they're compounds, okay? You've got multiple elements involved. If I look closely, you should notice that they're ionic compounds, okay? So you've got the cation in this first one is Ag, that's silver, and then nitrate is the anion. And then in the second compound, you have sodium is your cation, carbonate is your anion. So what kind of reaction did we say is typical when you have 2 ionic compounds? Okay, it's the one I wrote like this, AB plus CD. If you remember from the videos, I said when you have 2 ionic compounds, somebody said it.
Double displacement.
Double displacement. When you have 2 ionic compounds, A, B, C, D, what happens is the cation from the first one combines with the anion from the second, okay? And these are going to form a compound, what it would be, AD, all right? And the second compound is going to be formed, I'll pick a different color, let's do black. The anion from the first compound with the cation from the second. So then you would have plus CB, all right? So that is how you should predict your products. So go ahead and pair those up. The second thing you have to make sure you do is write the formulas correctly. You need to have charge neutral formulas, compounds. Okay, so how do we go about that? Well, I see silver is a transition cation on this first compound. What charge does silver carry, and how do we know? Anybody have a thought on that? Someone said
A +3
+3. How do we know?
from the polyatomic ion next to it.
So what charge does nitrate carry?
Just a negative charge.
A -1, right? Yes. So nitrate from your polyatomic list is this. So how many nitrates do we have?
Would it be 1 or 2?
We just have 1, okay?
Okay.
Because
Okay.
the formula is NO3, if we had more than 1 nitrate, you would have to have parentheses around that, right? And then you would have some sort of subscript down here. But we don't have those things.
Okay.
It's just NO3. So there's just one nitrate. So if we just have one nitrate here and it's got a -1 charge, total amount of negative charge is -1, right? And that means the total amount of positive charge for this to add up to 0 has to be +1. So how my cation here is silver. So my question is, what's the charge and how many do I have? Well, first off, how many silvers are in my compound? Just one. Okay, this 2 does not mean, it means for balancing purposes, we're going to end up with 2 molecules of silver nitrate, but within my compound, I just have 1 silver, 1 Ag, right? So I just have 1. So 1 times what gives you +1? There we go, +1. Silver's a +1. All right. Now the other one, sodium carbonate, is more straightforward. We know sodium is a main group 1, so there's no guessing on what its charge is. It's a +1. Carbonate, it's a polyatomic, so there's no guessing. It's a -2. All right, we know those. So now that we know the charges on everything, we can write the formulas correctly. So if we're going to have silver is going to combine with what? What's the anion on my other compound? It is carbonate. So I'm going to, silver and carbonate are going to combine to form my first compound over here. So it should be Ag. Now carbonate we said is a -2, silver is a +1. So we do the switch trick. Remember the switch trick when you go to write this out? We need 2 silvers and 1 carbonate. And then my other compound, we'll pick green, is going to be NO3 and sodium. Okay, now again, don't worry about balancing right now. You just want to get the formulas right. We'll go back and balance. So sodium is a +1 and nitrate is a -1. So we just need 1 each. Y'all may not be able to see that very well. Okay. Questions on how we wrote the formulas? I did a lot of this on the videos from last week, or some of it. I did a little bit of it. Okay, so there's our compounds. Now we need to know, are they going to be aqueous or solid? Are they going to be soluble or insoluble? So we need to look at our solubility rules. Okay, silver and carbonate. Let's look here. Do y'all see silver or carbonate anywhere on here? I don't. So silver carbonate is definitely going to be solid. Sodium and nitrate, if you go back and look at that, they're both on the solubility chart, and there's no exceptions, so they're definitely going to be aqueous. Okay. All right, now we need to balance. It's the last step. So if I'm looking at this reaction, let me erase all that. I forgot to take that out. Well, that one's already in there for you. We have 2 silvers in our compound on the product side, so we have to have 2 silvers on the reactant side. So we put a coefficient of 2 there. And another thing I noticed right here is we have 2 sodiums in sodium carbonate. So I need to have 2 sodiums over here. So I'm going to put a coefficient of 2 there. And then I think everything should be balanced. Okay, any questions? All right, well, let's move on to the second type. If you do have a question, feel free to put it in the chat. I can come back to it. If you want to email me, if you're confused on anything with this, there's a lot of information. There's a lot of thinking involved in these. These are not just like very simple things to do. All right, let's move on though. Number 2 is an acid-base neutralization reaction. Acid-base neutralization reaction. Okay, this commonly occurs between an acid, and here's how we abbreviate acid. We say HA. The A stands for the word acid. The H, okay, is an H+ ion. Okay, this is what acids donate in solution. If you are an acid, you have to have a hydrogen ion. You cannot be an acid without one. Every acid has an H plus in it, one that it can give away. So that's why we always write HA to indicate that. Okay, so it commonly occurs between an acid and a metal hydroxide. And we abbreviate that as M for metal. Hydroxide we know is OH minus. So MOH. And this is the base, the metal hydroxide. Now, I'll tell you this. There are other bases besides hydroxide. Okay, hydroxide is a really strong popular base, but there's other bases. So we'll get to that in chapter 10, but for now, this is kind of the generic equation I'm giving you. And what do they yield? Water and a salt, okay? So here is a very generic equation representing what we just talked about. Here's our acid, here's our base, and we're gonna form water, and this Ma over here, this is the metal cation with your anion from your acid, okay? The metal cation and the acid anion. And we get a salt. All right, tip. Here's what happens. The hydrogen ion, how do we form water? The hydrogen ion from the acid combines with the hydroxide ion from the base. H and OH give you H2O. Okay, so that's how we get water. Now, why do we call it a neutralization reaction? Because water has a pH of what? We actually haven't talked about pH yet, but it's pretty common knowledge.
7.
pH of 7, which is perfectly neutral pH, okay? We'll get to the pH scale later in the course as well. So because we're forming something with a neutral pH, that's why we call them neutralization reactions. All right, now the anion, guys, my writing, I'm sorry, it's horrible sometimes. From the acid combines with the cation, the metal is the cation part, from the base to get a salt. All right, that's what's happening. That's how you're forming your two products. So let's look at a real example of an acid-base reaction. We're gonna write out our products. So down here at the bottom in the red and the black text, we have CH3COOH. The red part is well, first off, this is your acid. The red part is an acetate anion. Okay, some of you might recognize it because it's one of the polyatomics that we know of. And the H, that's our cation. Now, I know what some of you are thinking, why are we not writing the cation first? Usually you should. Sometimes acids break the rules and the acidic hydrogen is written last, like you see here, but usually we do write the cation first, okay? So we have the anion is acetate and the hydrogen ion is the cation. And then we have our base is sodium hydroxide and the metal here is sodium. So I color coded these things differently so you can see which parts are gonna form your products. The red parts are gonna come together and you're gonna get sodium acetate. Okay, that's your salt, and this is aqueous because anything with sodium in it is soluble, if you remember from the solubility rules. And you're going to get water, H and OH. And that is a liquid, okay? So how do you know if you have an acid-base reaction on your hands? What's the telltale sign? If I give you an equation, I say, is it a precipitation reaction? Is it acid-base? Is it redox? That's what we're gonna talk about next. If it forms water, if water is one of your products, it's an acid-base reaction, okay? If you form water, how do we know if we have a precipitation reaction? If you look at your products and one of them is solid, notice we don't have a solid here as one of our products, okay? So this is how precipitation reaction and acid-base reactions are different, just by a quick glance. If you form a solid as one of your products, that's precipitation. If you form water, that's acid-base. Okay, so sodium hydroxide was our base here. All right, before we move on, let's do a practice. I want you to write out the acid-base reaction that's I've typed up below. Write the chemical formulas and then write what compounds you would get and write the states of matter with them. So cesium hydroxide, cesium is main group 1. It is CS. So try to write out your compounds, your reactants. And then based on how you know an acid-base reaction happens, again, it's 2 ionic compounds here. So these are also like a double displacement reaction, essentially. Cations and anions switching places. So hydroxide is OH minus. So there's all the parts for our reactants. I'll give you just another 30 seconds. Okay, so one of your reactants should be CSOH, right? That's cesium hydroxide. Is this the acid or the base? Cesium is the metal, the hydroxide is OH, so did we say that was the acid or the base? A metal hydroxide.
It's the base.
Yep, it's the base. Okay, and then the other one, to write a neutral compound, do the switch trick if you have to. You need 2 hydrogens, 1 sulfate. So it should be H2SO4, and this is your acid. It's called sulfuric acid, but it's also known as hydrogen sulfate. Okay, so if these are going to react, you can use the rules of a double displacement reaction, or you can use the rules we just talked about, the tip, okay, here, to form water and to get your salt. So we're going to have the OH part from the base and the hydrogen part from the acid are going to combine. Now again, don't worry about the fact that you have 2 hydrogens here. Just write water. You know how to write the formula for water. Okay, these are going to come together and give you water. We'll balance it at the end. And then the other part is we're going to have cesium and we're going to have sulfate. Cesium is a +1 cation. Sulfate is a -2. Okay, we wrote those up here. So we're going to need 2 cesiums. Okay.
Does it matter which compound we write first? Like if we were,
No,
it doesn't. Okay.
you could write cesium sulfate first if you wanted to.
Okay. Thank you.
So we know that water is a liquid, so we need to indicate that. And cesium sulfate, is it soluble or insoluble? Have to go look at your solubility rules. Sulfate's always soluble unless it's combined with barium, mercury, or lead. So we don't have barium, mercury, or lead, so it's aqueous here. Sorry, that is illegible. Oh Lord, I'm on like the massive eraser. Oh my gosh. Having a hard time here. There we go. Okay, so that's what you should have. All right. Any questions on this? Do we need to balance it? I think we need to go back and balance it. I see that I have 2 cesiums on the product side, so I need to have 2 over here. And that also means I have 2 oxygens and hydrogens here, plus I have 2 more hydrogens over here. So I've got 4 hydrogens total. So I need to double everything right here. So if I put a 2 in front of water, then I think I should be balanced. Okay, questions? We're about to talk about the last kind of chemical reaction. And before we do that, I like to spend a minute talking about why these reactions are important, because it's also the hardest to understand and label and predict and blah, blah, blah. So people tend to hate these reactions, but if you understand why they're important, I think you have a little bit of an appreciation for them, even though they're hard to do. So what do all these pictures have in common? First off, what are these things? What is in this picture right here that I just circled? Anybody know?
Is that a pacemaker?
It is a pacemaker. Dallas, that's the picture on the right. We'll get to that in a second. So if you see, I put this picture with the heart. This is a pacemaker. I don't know if you know anybody who's ever had to have one. My grandpa back in 2016, for almost a year, had a long bout with congestive heart failure, and it was complicated by pneumonia and a bunch of stuff. But he's in his 80s, and so a lot of times people with congestive heart failure, it's not very wise, the older they are, to do like an open heart surgery and put this in, or just do surgery on their hearts. And so there's medications that can help with your heart, but oftentimes if you can get a pacemaker, that really helps with just the mechanical impulses of your heart. So it's a pacemaker. It's run on a small battery. Next over, this picture on the right with the girl in the ponytail. Dallas said it in the chat. She said it's a cochlear implant. So people who are deaf, they can get one of these, and this helps stimulate auditory sensation. It doesn't mean they can all of a sudden hear perfectly, but it helps them with auditory stimulation. Or people who experience a lot of vertigo, it just helps with equilibrium as well. You can get a cochlear implant. And then picture on the bottom, it looks like we have a veteran here. And so a lot of times, you know, or you may have someone in your family who is a veteran, and they can, depending on their experience in war or in their division or whatever, in their ranks, can deal with PTSD. Okay, and you don't have to be a veteran to deal with that, obviously, but people who deal with this, they can have different mechanisms installed to help with nerve impulses. Okay, now obviously that's not a decision you would take lightly, because it also might make you feel like a little bit of a robot and not have the freedom to feel things naturally, but it can help with PTSD. And so all of these devices, they're life-changing, right? And what do they all have in common? They all run on very small batteries. Okay, so the point I want to make is that batteries are really important. Now, how does a battery work? Anybody know? Obviously, batteries go beyond just these devices I've shown, but I tried to pick things that are related to health sciences. Batteries run on redox reactions, okay? So that's what we're getting into next. The last kind of reaction we're going to talk about is known as an oxidation reduction, and you abbreviate it redox reaction. Oxidation reduction reactions, redox. Now, in an oxidation reduction reaction, it's one in which electrons are transferred from one atom to another. I'll go back to green. So you guys are familiar with electrons being transferred. This is nothing new. So if I can simplify this kind of reaction in any way, know that you're familiar with electrons being transferred. Now, you're familiar with it in the sense of forming cations and anions. And we're not directly talking about cations and anions here. We're more so trying to track what substance is increasing in charge and what substance is decreasing in charge when an electron is transferred. Okay. These blanks down here, the two portions, oxidation. This is when you lose electrons. Okay, think about what's going to happen to your charge if you lose electrons. Is your charge going to increase or decrease? What's going to happen if you are neutral? You have zero charge and you give an electron away. What happens to your charge? Does it increase or decrease?
It becomes more positive.
It becomes more positive, so your charge increases. Okay, so here, I'm going to say charge increases. I'm not going to say charge is positive. Why? Well, let's look at this figure on the left. If we look at this very top, this is a figure from your textbook. Let's say I'm an anion with a -2 charge, and I give away an electron. Guess what? I'm still an anion, but now I'm an anion with a -1 charge, and I gave away an electron. that is oxidation because I gave one electron. I'm not positive, but I was oxidized, okay? So I don't want you to get in your head giving away electrons means you form cations. That's not always the case. Okay, reduction, on the other hand, is the gain of one or more electrons. So what happens to your charge if you gain electrons?
The charge
Become
decreases.
It decreases. I'm not going to write that you always become negative because that's not the case either. So your charge decreases, okay? An example, if we follow this figure, so for oxidation, if you want to see any example of oxidation 4 different ways, follow the figure from left to right, okay? Start with these on the left, follow it to the right. That's oxidation, okay? If you want to see reduction, you start on the left, or start on the right and read it right to left. Read it backwards. You have an electron. When you add it to a species that's +2, for example, down here on the bottom, the charge decreases by 1. You're not an anion just because you receive an electron in this case. But your charge was reduced from a +2 to a +1. Okay, so these are just examples of how oxidation and reduction can occur. I put this phrase oil rig down here because this is how it helps a lot of people memorize the process of oxidation and reduction, and it keeps you from getting it confused. Oil means oxidation is loss of electrons. Rig is reduction is gain of electrons. In both cases, of electrons. Okay, the confusion, when you say you gain electrons, it sounds like you should gain charge too. But remember, because electrons are negatively charged, gaining electrons decreases your charge. All right, questions on how we define oxidation and reduction? So we're going to look at some real examples now with different chemical reactions. And the question here we're trying to answer is we're trying to identify what element is oxidized, what element is reduced. So let's look at this. We have copper, it's a solid, and we have silver nitrate, it's aqueous. And we're forming plain old silver on the product side, and then we have copper nitrate. So first off, if we had to classify this as like a combination, decomposition, single displacement, double displacement, or combustion, how would you classify this reaction?
Is it double displacement?
Close, but no. Double displacement is when you have 2 full-on ionic compounds. I have 1 ionic compound and I have 1
Single?
element. Yes, Ashlyn in the chat, it's single displacement, okay? It is a displacement reaction, but it's only single displacement. The key sign that I talked about with single displacement is you have something by itself, you have like a pure element, and then you have 1 ionic compound, okay? And what we see is the copper is displacing silver, okay? These test tubes over here actually show you what happens if we were to do this in lab, okay? You have a copper metal wire in this silver nitrate solution, and as you let it sit, this gray stuff that you're forming is the silver, and then you see how the solution has turned blue a little bit? That's what copper does to things, right? My husband, his very first wedding band was a copper wedding band. That's just what he wanted. And so he has since gone through many. Now he just has it tattooed on his hand because he can't keep up with the rings. But the copper kept turning his finger like green. It was actually kind of gross. But every time he'd like wash his hands. So if you ever have copper jewelry, sometimes earrings or earring back rings can be like copper and stuff. Be careful because if it gets wet, it definitely will. That's just what copper does. In solution, it turns things like a bluish, greenish color. Okay. All right. So let's look at what's happening. Here's our questions right here. What happens to copper? What happens to silver? Well, copper, initially, when things are by themselves, like in their elemental form, as you would see them on the periodic table, they don't have any charge. They're just neutral, right? They're not a cation or an anion. So starting out, copper is right here. Copper is just a solid, plain old copper by itself. It's not a copper cation. It's just plain copper. So what we say is initially starting out, copper has a charge of 0. Okay, I'm looking right here. On the product side, let's look. Oh, sorry. On the product side, copper's over here. Copper is now a cation. How do I know that? It's in a compound. So what charge does copper have as the cation? And how do we figure that out? Well, you have to look at what anion is involved and how many do I have. Okay, I have nitrate, NO3. We said NO3 is a -1 charge. And I have 2 of them. So total, -1 times 2 means I have -2. Well, I only have how many copper cations? I just have 1, right? So that means to balance and make this a charge neutral compound, that copper has to be +2. So that's what we see over here. We go from 0 charge to +2 charge. That's what copper's doing. So let me ask you, did copper gain or lose electrons? Copper is going from 0 to +2. So did it gain or lose?
It lost electrons.
There's disagreement. Someone said gain in the chat. Aubrey said lost. Gain, gain. Morgan saying it gained electrons. Remember, electrons are negatively charged. So if you gain an electron, what happens to your charge? Oh, Dallas said lost. Okay, so it lost. Loss of 2 electrons. Okay, go up and look at that figure again if you get confused. Okay, when you lose electrons, your charge increases. Remember, that's what oxidation is. It's the loss of electrons, and we said charge increases. And that's what's happening with copper here. We lost 2 electrons, so its charge is going from 0 to +2. Charge is increasing. So is copper oxidized or reduced? Remember, oxidation is a loss, so this copper is oxidized. Okay, you could write that up here as well. What happens to copper? It's oxidized. All right, now let's look at silver. Silver initially is right here. It's a cation, right? What's the charge on it? It's a transition metal, so how do we know? Well, we look at the anion, we have nitrate. We said over here, nitrate is a -1. It's still a -1, that doesn't change. We only have 1 of them though, in this compound. On the product side, we had 2 when it was combined with copper, but here we only have 1. So that means silver is a +1, starting out as a cation. All right, so on the reactant side, it's a +1. Well, what is it on the product side? On the product side, it's just by itself. It's just plain old silver. It's not in a compound. It's not a cation. That means it's 0 over here. No charge. It's neutral. So what happens to silver? It goes from +1 to 0. And that's what we're pointing out with these phrases right here. +1 charge to 0 charge. So the question is, did silver gain or lose electrons? Meredith said gain. Dallas said gain. Yes. So if you gain electrons, remember, oil rig reduction is the gain of electrons. So what happened to silver? It was reduced. So how do you, these are complicated. I try to warn you, these are the most complicated we're going to get into. And how do you go about these? Well, you have to look at the reaction that you're given. And you have to assign, see how we assigned all these numbers? And in this figure, we're calling them charges. In actuality, they're called something else. We're going to get to that in a slide in just a second. You have to look at your reaction. You have to assign all these, quote, charges or oxidation numbers. And then you have to see what's increasing in charge, what's decreasing in charge. Okay? Once you do that, then you just figure out which one, you see which one was oxidized and which one was reduced. Okay? That's how you go about these. They're not as straightforward. You can't just look at the product and think, oh, do I have a solid or a liquid or a gas, so therefore it's whatever. No, you actually have to dig into it. You have to assign these oxidation numbers. You have to see which element is increasing in charge, which element is decreasing in charge. There's just no way around it, okay? Redox reactions involving ionic compounds are usually straightforward. Don't you love it when we make it sound simple? They're straightforward, guys. They're not straightforward. But when you know the steps are straightforward. It's just there's a lot of steps, okay? What we're doing is we are looking at the change in charge. Okay, to summarize, we're looking at the change in charge. And that's how we're determining what is oxidized, what is reduced. So to be good at redox reactions, you have to be good at assigning the charges on the reactant and the product side. So let's do another one. We're quickly running out of time, but I think if we can get through this slide and the next one, we should be good. So we have this reaction right here. Ki, that's potassium iodide, and that's an ionic compound. And then we have bromine by itself, plain old bromine, just an element here. Now it's a diatomic, okay, so that's why we wrote the 2 there. Don't forget your diatomics. On the product side, we have iodine, and then we have potassium bromide. So again, this is single displacement. So a telltale sign that you have redox is that you have a single displacement reaction. All right. In single displacement, something's always changing charge. So that might get you through a question of what kind of reaction is it, but if I ask you to tell me what's oxidized and reduced, you still got to know the rules to answer those kinds of questions. So what happens to, this is a typo, this should be bromine. What happens to bromine? What happens to iodine? Which one's oxidized? Which one's reduced? If you'll notice potassium, the K, potassium is a cation on both sides. It's a +1 on both sides. So there's no change in charge for potassium. All right. We kind of call ions like that spectator ions. They're not really playing in the game here. Nothing's changing. So if we look at iodine, okay, on the reactant side, iodine is an anion. And we know iodine's very predictable. It's always a -1 charge. So it's a -1 here. But then as an element on the product side, it has a neutral charge, no charge. So what happens to iodine? Well, we just said it goes from -1 to 0. And that's exactly in the red text down here. That's what it's pointing out. We have a minus charge when it's an anion in a compound, but when it's by itself, when it's just an element, no charge. So did it gain or lose electrons?
Lost.
It lost electrons. And we said losing electrons, your charge is increasing here. That is oxidation. I'll say it's oxidized. All right, bromine. Bromine is just, let's look at our reaction. Here it is right here. It's just by itself. It's just an element. So anything that's by itself, just an element, no charge. It's neutral. When it's on the product side, though, we see it's in a compound. That means, and it's written second, so it's an anion. Bromine is a halogen, just like iodine, so it has a -1 charge. So what happens to bromine? It goes from 0 to -1. And that's exactly what you see in the blue text, 0 to -1. So did it gain or lose electrons?
Gain.
Gained. So bromine was reduced from 0 to -1. The charge was reduced. And so to summarize the bullet points down below, here's what's happening. An iodide ion is going to give an electron. Bromine's going to pick that electron up. So an iodide ion is, we said, oxidized. As its charge increases from -1 to 0, bromine is reduced. As its charge decreases from 0 to -1. Okay? So that's essentially it. There's several more slides. We're going to talk about oxidation numbers real quick. We're not going to get to these today, but I put a lot of examples for you to try to practice on your own. I was going to make a poll question about that. Do you guys have these in your slides from Blackboard, the ones you downloaded? Do y'all have these practice problems right here? Anybody download the slides? Okay. So you can practice those or attempt them. I'll probably, I don't know, I'm going to try to come up with something we can do to give you the solutions for these. But then there's some slides down here. These are kind of just summary slides. I don't know if I'm going to make a video about them, but really if we don't cover it, don't worry about it for the exam. Okay, let's talk about oxidation numbers before we're done for the day. So we've been talking about, I've said in the figures up here that we've been talking about a change in charge. You see the word charge on everything I'm circling. But I don't necessarily want you to think of it as charge, okay? I want you to think of these as oxidation numbers. And I think what would be most helpful is once this lecture finishes, if you'll just literally after lecture go take 5 minutes. I know your brain is probably fried, so maybe do it later tonight before you go to bed. Take 5 minutes and review page 151, 152. This is in your textbook. This information we're about to talk about is directly out of your textbook, okay? So please go read it as well beyond what I'm just saying so that you get a full understanding. So what is an oxidation number? It is a value, okay? Notice I'm not using the word charge. We're just saying it's a numerical value that we assigned to elements to indicate whether they are neutral, electron rich, or electron poor. Okay, if something is electron rich, has a lot of electrons, it probably has a negative charge. Something is electron poor, it's given away electrons, it most likely has a positive charge, but not always. So this is oxidation numbers. They do not necessarily imply ionic charges. They're very similar in most cases, okay? But it's just a little bit nuanced. We have to think of them differently. So here's some rules, because the whole key to getting a redox reaction correct is doing what we did up here. See all these numbers? These are oxidation numbers. If you can assign these correctly, then you can do redox easy peasy. So how do we assign oxidation numbers? Well, an atom in its elemental state, guess what we did? Every time we saw something by itself, what number did we give it? 0. So it always has an oxidation number of 0. A monatomic, what does that mean? That means an atom, a single atom ion. Mono was the prefix for 1, if you remember, when we named binary covalent compounds. So a monatomic ion, an ion that is just one atom, not a polyatomic, monatomic. It's going to have an oxidation number equal to its charge. Okay, that's why these are so similar to charges. They're basically charges, we just call them oxidation numbers. So for example, chlorine, when it's an element, we know it's diatomic, it's going to have an oxidation number of 0. If it's an anion, what would the oxidation number be for chlorine? Well, if it's an ion, if it's an anion, we know chlorine is Cl minus 1. So the oxidation number, what rule number 2 is saying, the monatomic ion chlorine, its oxidation number is the same as its charge, so it'd be a minus 1. 3, in a compound, an atom usually has the same oxidation number it would have if it were a monatomic ion. Okay, now let's just say that we have chlorine with magnesium. We have chlorine, it's just in a compound. What oxidation number do we give chlorine? Rule number 3 is saying it would usually have the same oxidation number it would have if it were a monatomic ion. Well, when chlorine was a monatomic ion, we gave it an oxidation number of minus 1 because that's what charge it carries. So all rule number 3 is saying is even when it's in a compound, we still give an oxidation number of minus 1. So you think about what would it be if it were a monatomic ion, you give it that oxidation number. And then lastly, the sum of oxidation numbers in a neutral compound is 0. In our last minute, let me use HNO3 as an example. If you're ever trying to figure out, like right here, if I were to ask you, what's the oxidation number on nitrogen? As an anion, nitrogen is usually a -3, but it doesn't line up here. If you actually look at this compound, this is an ionic compound. H is a +1. NO3, we know, is an anion. It's a polyatomic with a -1 charge. So we actually have to dig into nitrate to see what's the oxidation number on nitrogen. Okay, it's not -3. Why? Well, oxygen usually never deviates. Its oxidation number always matches what it would be as an anion. Does anybody know what charge oxygen carries as an anion? Oxygen is main group 6. Anybody remember what charge is oxygen going to carry as an anion? Meredith says -2. I agree. It's a -2. Okay. So if we're just looking at nitrate here, okay, oxygen is a -2. And we have 3 oxygens, and each one is a -2. So total, how much negative charge is that? -6. Well, overall, nitrate is a -1, right? That's what we drew right here. We've memorized that from first week of class. It's a polyatomic with a -1 charge. So that means -6 plus what gives you -1? Because the only thing we haven't figured out yet is what nitrogen is carrying. And this is where oxidation numbers are different than charges, because here, oxygen is a +5. Sorry, nitrogen, not oxygen. So the oxidation number on nitrogen in this compound is a +5. Okay, and that's bizarre. Usually it's a -3 as an anion. But because the sum of the oxidation numbers has to add up to 0, there's ways you can go through and look at it and calculate and figure out what it should be based on what things you know are. Okay. All right, so that's oxidation numbers. I've gone like 2 minutes over now. Sorry, everyone. If you have questions, I will stick around. That's it for today.